Good morning, eighth graders. So we are getting into the portion of astronomy that I think most of us think of when we think of astronomy, and that is what's going on in our solar system, what is out there in space. So we are working with, finally, Middle School Earth Science Standard 1-2, which states that you'll be able to use a model to describe the role of gravity in the motions within galaxies and the solar system. We have talked gravity at this point in time, okay? But I want you to kind of put that off to the side of your forethought and let's just focus on the solar system so we can understand what we're all working with. So by the end of this unit, you should be able to analyze and interpret data to determine the scale of objects in our solar system, develop and use a model to describe the role of gravity in the formation of our solar system, as well as support your claim with evidence and reasoning to demonstrate that gravitational interactions are attractive and depend on the mass of the object. Okay, so we're going to start taking the portions that we didn't cover in gravity and start kind of making those dots so that hopefully in a couple of days we can start connecting them all. You should have your notes page in front of you, whether it is the lecture, whether it is the textbook, whether it is the video, whatever works best for you. But whole group is all the same. So let's talk about what people's thoughts were prior to true understanding. So we used to believe, because humans are very egocentric, meaning that everything should just revolve around us, we used to believe in what is called a geocentric model. Okay, geo meaning earth, geology is the study of earth, centric meaning center. Okay, this is what the early Greeks thought our planets, the sun, the moon, and all of the stars used to be set up as. If you take a peek in this diagram, you can see that we believed Earth was there and everything else moved around us. Now, why would we think this way? Well, we back then only saw the sun moving across our sky. So why would we be moving if we can physically see that happen? Okay, we aren't feeling the actual rotation and revolution of the earth below our feet as we stand here or sit. Okay, and the technologies that they were using were very basic. When I say technologies, I am meaning like very rudimentary or very like scaled down telescopes, but it was mainly just observation. So using your actual eyes to be able to watch the sky and what's going on. Okay, so that was the geocentric model, where we were the center of the universe, because why not? It wasn't until Nicholas Copernicus and Galileo, they changed the idea of a lot of things, and that is because they developed what we now know as the heliocentric model. Helio meaning sun, centric being center. Because what they did is they observed the moon. So we've already talked moon phases. They observed that the moon was changing as it moved. So the idea that we still saw the moon every night, minus the new moon, but you can still kind of make out where the moon would be sitting. So they're like, well, if we see it every night, no matter where we are at on the planet, we must be thinking about this all wrong. The Earth isn't just sitting there, but rather the moon is going directly around the Earth. And it must be moving in a way that the Earth is moving, or else we wouldn't see the moon all the time. If we weren't rotating as well, at the same rate that the moon is revolving, there would be some nights where only people on the eastern hemisphere could see the moon, and opposite of the western hemisphere where we live, that sort of a thing. So they started observing those things, and then they started kind of charting other things in the sky that was moving. You can see Mars, Venus, you can even see Jupiter, sometimes Saturn, in our night sky, to where they started seeing these dots that would just shift ever so slightly across our sky. But the one constant was always the sun. The sun was always big and bright and in your face, minus like cloudy days, and all this. So this is when they then showed the idea of a heliocentric model. Now, people thought they were crazy, okay? But after better technology and better data was actually collected and used, that is how we then determined this is the true thought process. We are not the center. So that, and then you get like with Galileo Galilei, you get the idea of gravity coming in and all this to where it's like, well, how could everything be revolving around us? So that's just kind of the like progression of moving from a very geocentric model idea to a heliocentric model. So we obviously know when I say, hey, what's in our solar system? Typically, I get learners who are telling me sun, planets, okay? But there's so much more out there. Not only do we have the sun and our 8 planets, but we also have satellites, both man-made and natural. We have dwarf planets. Pluto is out there still. We have asteroids and comets. We have technically meteoroids until they start making their way into atmospheres. But we'll talk about that. So these are the 7 main objects we are going to talk about within our solar system. But know that there could be so much more. And each of these, minus the sun, each of these have thousands potentially within our solar system. So let's talk about the sun. Okay, I'm not going to spend a whole lot of time on this because we literally spent a whole day on it, like just the sun and the earth, back in our seasons unit. So let's just talk about the sun, but more so importantly, the role the sun plays within our solar system. So the sun itself is a large ball of burning gas held together by gravity. Its core is so hot and getting so much gravitational pull at it that nuclear fusion is actually what is occurring. So I was asked the other day in class, well, does the sun have a core? Yes. Could you stand on it? Yes. Technically, it does have some solidity to it, but it's really, really hot, and that's literally where all of the sun's power is being created. So that, so nuclear fusion, and that is what keeps the sun alive, is these different atoms coming together and creating this immense amount of energy. So because the sun is so massive, we've talked, it's 99.8% of the entire mass of our solar system. That leaves only 0.2% to everything else in our solar system. Okay, so it's massive compared to anything else. You can't even put everything else together and it equal the mass of the sun. Okay, so because it's so massive, its gravitational pull is what keeps the entire solar system held together in this neat little ball, essentially. So that is the sun. Its role is to provide us with energy. Its role is to keep us in our places, and that sort of a thing. So that's the sun. If you're only here for the whole group portion of the notes, I'm done. Okay, so hopefully a little less than 10 minutes wasn't painful. As you progress through the rest of this lecture, please make sure to keep your CHAMPS expectations in mind within the classroom. And yeah, if you're still here for the rest of the PowerPoint, stick with me. Let's keep going. So I'm not going to spend a lot of time on the planets because we're literally going to spend like the next 2.5 days talking about the planets. But let's talk about them within our solar system and how they got to be as magnificent as they are. So there are very specific criteria that an object in space must meet in order to be considered a planet. Okay, so these criteria is what eventually led to the demotion of Pluto, but then also has kept it to where it's just these 8 planets. So there are 3 criteria. First, they have to be of a certain size. Okay, they have to be large enough, okay, to have enough gravity to force it into a spherical shape. Okay, so I'm not saying that it has to be at least X amount big, because Mercury is gargantuan, Mercury. Mercury is just itty bitty, and Jupiter and Saturn are gargantuan. Okay, so there is no minimum to maximum sort of thing, but they must be large enough to be able to have enough gravity to force them into a spherical shape or a ball. Okay. Second criteria, they have to orbit our star. Okay. Now, when we are talking our solar system, yes, we're talking the sun, but there are other solar systems and other galaxies that they have planets that are orbiting their star. Okay. So all 8 of these planets have made it to where they are orbiting around the sun. Okay. Now, finally, they can't just orbit, but they have to have cleared away every other object within their orbit. Okay. So what that means, let's think back to what an orbit is. An orbit is essentially a pathway. So if we think of the 8th grade hallway as our orbit, it is as if one person alone were to be out in the hallway walking around, and they're the only ones. Okay? That is clearing away all other objects within their orbit. Okay? So we have our 8 major planets that revolve around our star. We have the 4 inner planets. That would be Mercury, Venus, Earth, and Mars. We also refer to them as our rocky planets. And then we also have our 4 gas, outer gas giants. And I guess gas isn't the most eloquent term for them anymore. So we have talked about them as our gaseous planets because Jupiter and Saturn are gas, but Uranus and Neptune are actually solid ice because of how cold they are. But if they weren't as cold, they would be made of gas. So gaseous is apparently the more eloquent term. So that's all we're going to talk about with the planets. But you need to know the 3 criteria that gets a planet to being called a planet. Satellites. Now, when I say satellites, learners typically start thinking like the man-made ones, the ones that we like shoot off into space, and this is what we use for things like communication and internet and research and things like that. But a satellite, if we were to define just satellite, it is an object that orbits another object in space. Okay? We as a planet are technically a satellite of the sun. Okay? Our moon is a natural satellite of the Earth because it is not on our orbit. It is actually orbiting around us. Okay, so we can consider natural satellites things such as planets, moons, asteroids. Hello. So I am recording this in case I use it in years to come. I'm recording this in September of 2024, and we actually have an asteroid that is starting to come into our gravitational pull. It should be officially snatched up by the Earth here on Sunday, but it is an asteroid that's coming in, and it's going to be stuck around us as a natural satellite for a couple of months before it slingshots back out. Its true orbit is around the sun. So it is a satellite of the sun, but we're going to catch it for a couple of months. It's too small for us to actually see with the naked eye, but it's kind of cool to be like, hey, we have 2 moons for a little bit. So those are the sorts of things that would be considered natural satellites. Now, we do have artificial satellites or man-made satellites. These are the machines that we launch into space to orbit the Earth or other planets in order to gain information. Now, these can be satellites that we use for communication or internet, but most importantly, these are satellites that we use for research. The James Webb Telescope is technically a satellite that we're sending out to try to take as many pictures as possible of everything out there. And all that sort of a thing. I guess you could kind of consider the International Space Station as a satellite. It is an artificial man-made satellite, but it's out there. It's orbiting free-falling-ish of Earth. Okay, so those are satellites. So when we say satellites, we're not just talking about the metal and wires and things like that, but we're also talking about moons and asteroids. So those are our satellites. Dwarf planets, and this picture just kills me. So, dwarf planet is probably one of our newest terms in relation to how we talk about things in space. So, this was a new classification that was added back in 2006. So yes, I am a 90s kid who grew up with the 9 planets, and Pluto was always a part of it. But you guys have now grown up, since you weren't even a thing yet in 2006, with there only being 8 planets. So what classifies a dwarf planet? Well, this is where they have just enough mass and gravitational pull to be kind of sphere-ish. What do I mean by sphere-ish? Well, Pluto is round. It is like a ball. It had enough gravitational pull to create itself into an actual sphere. Things like, I believe it is Makemake, which you can find within the asteroid belt, is more like an egg shape. It's more elongated. But it is technically considered a dwarf planet. It's sphere-ish. They also get this title by being similar in mass to the orbit, to what is kind of within its orbit or orbital path. Most dwarf planets do not have a cleared orbital path. So Pluto can be found within the Kuiper belt, right outside of Neptune. And it actually makes a path that crosses over Neptune's at one point in time. So if it weren't for Pluto, Neptune would have a 100% cleared out orbital path. That Makemake, like I said, is within the asteroid belt between Mars and Jupiter, to where it's stuck with a bunch of other similar sized sort of masses around it. So those are dwarf planets. Okay, I don't know. I have a heart for Pluto. I miss having Pluto as an actual planet, but it is technically a dwarf planet now because it just doesn't meet the actual classifications of a true planet according to the new 2006 classifications. Asteroids. I've kind of made note to this now. So asteroids are these small rocky bodies that orbit the sun. We mainly find most of our asteroids within our asteroid belt, which can be found between Mars and Jupiter. Okay. The weird thing about these is that they don't really ever stick together. Okay. If we were to imagine the solar system pre all the planets, most of the time the solar system look like this, where you had a bunch of little rocks within one orbital path. And eventually they start to kind of clump together, and that's how we then created our planets. But because of the sun's massive gravitational pull, countering by Jupiter's massive gravitational pull, these rocks don't ever stick together. They hit each other, and you can actually like hit an asteroid out of the asteroid belt, and that's how they come closer to us and things like that. So because of Jupiter's gravitational pull, it doesn't really allow for the clumping to happen. So you can see from this diagram, you have the main asteroid. Oh, I don't know why I'm trying to show you with my hands. That's silly. You have the main asteroid belt that is found between Mars and Jupiter. You also have what we call the Trojan asteroids, and these are the asteroids that Jupiter just can't get rid of. Okay, things like that. But just beyond Neptune, we have another asteroid belt. We just don't call it that. We call it the Kuiper belt. And that is where we're able to find Pluto. So it's just another very similar like idea of this, but just out beyond Neptune. So those are asteroids, just small rocky bodies that just kind of hang out. And because of everything else, they don't clump. Comets. Comets are really cool. So comets are a mixture of rock, ice, and dust because they tend to be much further out from the sun a majority of their life. They're loosely held together with a gravitational attraction. So they're still within the sun's orbit, but they sometimes go so far out that they're more of just kind of like, if you think of cotton balls kind of clumped together, where if you hold them a certain way, yes, they'll stay kind of spherical, but as soon as you let go, all of them fall apart, that sort of a thing. So they're loosely held together by gravitational attraction. And they have these really long ellipses. So an ellipse is essentially this long egg-shaped path, to where in the case of a comet, you have the sun here, whereas with us, the sun is more so like there. Okay, that little dot, that's where the sun ends up for us. But with this really long ellipse, it's able to like go way out, but still have enough gravitational pull to start coming back in, and then boom, you get that like boomerang sort of effect that we've been talking about for a couple of days now. Okay, so those are like kind of what makes up a comet. Now, this is what's kind of cool. The actual structure of a comet, I think, is weird to think of. Okay, so the comet has a solid inner core, just like any of our planets, our asteroids, things like that. There is a solid mass in the center of it. This solid mass is usually that rock and gas and ice, to where as the comet starts coming back in toward the sun, all of that ice turns into gas. And the gas and dust start to move away from the nucleus, making it glow. And that's why we get these streaks across our sky. So it's the glowing nucleus, which we also call a coma, that is streaking across our sky. And that's because essentially we are evaporating off we're melting and evaporating off all of the ice and gas to create this little bit of like a spark. So yeah, those are comets. Halley's Comet, there's a couple others that literally are just letters and numbers put together. There are two different types of comets. We have short-term comets and long-term comets, and all that really comes down to is, where do they go when they're away from the sun? Okay, so short-term comets typically don't go much past the Kuiper belt or past Neptune, whereas long-term comets can go out as far as our Oort cloud, which is the final sort of like outer shell of our solar system. So comets are just so cool. Final objects within our solar system, and I say objects very loosely. This is one object, okay, a meteoroid, but it gets 3 different names depending on where it's located. So meteoroids, meteors, and meteorites are all the same thing, okay? So a meteoroid, let's just define it as itself right now. It is a small rocky particle that moves through space. Okay, so we find meteoroids out in space. Okay, they're about between the size of a grain of sand to sometimes as large as a golf ball. So they still don't get very big. It's just random space dust and junk that gets caught up. Once the meteoroid starts entering into an atmosphere, okay, if we think of Earth, for instance. So as soon as it leaves what we define as space and it starts entering in our atmosphere or the gas around us, that is when it changes its name from a meteoroid to a meteor. Okay, we can see meteors as a streak of light that comes across our night sky. They're made up of glowing meteoroids. So it's essentially, again, similar to a comet where it's coming into our atmosphere, so we start to burn off all of the ice, the gases, things like that. Once a meteor then falls to Earth, okay, so the second that rock touches Earth's surface, it is now considered a meteorite. Okay, a meteorite is a meteor that has successfully survived a trip and made it to the surface of whatever object it was being like hurtled toward. Okay, meteors and meteorites aren't just found here on Earth. The moon has craters because of all these meteoroids that it pulls in through its gravitational pull, burns up in its minimal atmosphere, and has crashed onto the actual surface itself. So these can happen on any planet, on any satellite, whatever. But if we're just thinking for our sake, okay, a meteoroid is in space, a meteor is coming through our atmosphere, and a meteorite is when it has reached Earth's surface. Okay, so again, same thing, just different locations. So yeah, so those are like the 7 different objects we can find within our solar system. Just kind of little more tidbits of information. A lot of this you probably kind of knew, but we again just give it an 8th grade definition. So yeah, that is it for our notes. So make sure that you have completed your notes. Make sure you submit them properly. Double check to see if there is a check-in that goes along with this. And then we will start talking about our actual 8 planets tomorrow. So fabulous. Thank you so much, 8th graders. Have a super awesome rest of your day, and we'll see you soon. Bye.